Alrighty, hi everyone. This is the 2022 TGC Derived Grade Organic Level 3 exam. Again, refer to the mark schedule for more detailed answers. Right, so our first question is a pretty standard naming and drawing. So we've got 1, 2, 3, 4, 5 as a pent. This carbonyl group here makes it a ketone, and we do have a choice of places where the ketone group could go. So we want pent and 3-one. So that's the ketone bit. That's where the ketone is. Do not forget the an. You will get it wrong if you don't put that in there. It's not pent 3-one. Right, so butanoic acid. Let's start with but 4 and the carboxylic acid on the end carbon. This question is designed to see if you know where the 1 is. That's the first carbon. So the 3-chloro has to be off this carbon here. I'm not going to put all the hydrogens on. You will do that in your exam just for speed today. Right. 2-hydroxypropanamide. So we've got propanamide. So that's 1, 2, 3. And anamide is an amide, CONH2. And we've got a hydroxy, which is an OH group off carbon 2. Okay, and just complete all the hydrogens. I did draw them here. No hydrogen off that carbonyl carbon. This one here, if we look here, we've got an ester group. We have got 3 carbons off the oxygen end and only 1 carbon off the double bond end. So that gives me propyl for this bit here and methanoate for this bit here. Okay, right. We are going to distinguish now between these compounds here. So this is a pretty straightforward one. We've got a ketone for E and an aldehyde for F. And we need to use Tollens, red or blue litmus, or water. In this case, we are going to use Tollens. We are going to give the conditions. So you could put that is ammoniacal, silver ions. So silver ions and ammonia, and we do warm that. We would see a silver mirror appear, and you're going to write this in sentences, but I'm just going to bullet point it. For compound F, no silver mirror for compound E, and a reason for the reaction. So compound F is an aldehyde, so can be oxidized. This is a ketone, cannot be oxidized. So that's your reason for the reaction based on the functional group. And structural formula for the product, well, this is the one that can be oxidized. So it's going to be 4 carbons still, 1, 2, 3, 4. Oxidation in organic is just adding oxygen. So we're going to make that into a carboxylic acid. Just make sure we've got all our carbons there. Right, up here for compound G and H, we've got an acyl chloride. And we've got an ester. So the best thing we're going to add here is we're going to use water, and most of you did get that. So if we add water here, we do not need any conditions for that. We are going to get with G, the acyl chloride, a vigorous reaction. We are going to get bubbles or fizzing, and we are going to get steamy white fumes. With the ester, we will get no bubbles and no fumes. We do need to state that. We might see 2 layers form with this one. That's a bit of an added extra. We need to give a reason for the reaction. So we just need to say this can undergo a substitution reaction, as this is a reactive acyl chloride group where the Cl is substituted for an OH from the water. And therefore the product is again... Oh, actually, it's only got 3 C's. Where's my rubber? Is propanoic acid. Okay. This one here, we do need to do 3 reactions. So we're forming an amide. Here is our amide group here. So we do need to form an amide in each of those or react the amide. So, too many of you decided that you'd start with an amide to make an amide. Remember, we want to add something that looks like that and something that looks like that. So what we want is an amine that looks like that, CH3. I'm just going to copy that, CH3, and I'm just going to make that into an amine, NH2. And we want something that will react with an amine. It could be a carboxylic acid. That's a little bit more complicated. I'm going to go for an acyl chloride here because that will react more readily. If it was a carboxylic acid, you could get that. It would just need a few more conditions because otherwise, if this was a carboxylic acid, you'd just get an acid-base reaction. We needed to recognise here that these are both hydrolysis. This is an acid hydrolysis. This is a base hydrolysis. So we need to draw that line right down the middle of that functional group, and we need to separate. So CH3CO and CH3CH2, CH2NH. And we need to complete these functional groups in acid situation. So this will be OH and this will be NH3+. Right, you don't have to draw it out like that. That's just the way I prefer to do it. We're going to repeat that. So we're going to separate where we've drawn that line. Oops. Okay, and then we're going to complete these functional groups in basic kind of situation. So we've got O- there and NH2. So fully protonated up here, fully deprotonated down there. Okay, right, over the page. So this one here, explain why this compound can exist as a pair of enantiomers. So we need to identify a chiral carbon, which is going to be this carbon here. So we need to state that there is a chiral carbon with 4 different atoms or atom groups attached. I would probably tend to say what they are, that, the hydrogen and that. And because it's got a chiral carbon with 4 different groups attached, it can form 2 mirror images. That's a pretty straightforward question. Drawing the optical isomers. So I would start with a mirror line, then I would do the chiral carbon, I would draw out the geometry so that it's mirror imaged. Okay, and then I'm just going to put the same atom or group there, so let's just put the H up the top. Same one here, CH2, CH3, so quite a few of you put the CH3 and then the CH2. That can't happen. Try and draw it out. It doesn't work. And this needs to be a CHO, not a COH. Sorry, you couldn't see that. This needs to be a CHO, not a COH. I'm actually just going to draw that out so I don't need to worry about that. Okay, on the same one. And then my last one's an OH, making sure the O is attached to the carbon. So there's my answer there. That's a nice easy mirror. Okay, so this is some isomers. So we've got J, which is C4H8O2. So it needs to be a straight chain. So I'm going to put 1, 2, 3, 4. Same functional groups, right? And compound J is up here. What are the functional groups? Aldehyde and alcohol. Right, some of you didn't go back up there and have a look at that. So it needs to have the same functional groups, but no enantiomers. So there's nowhere else I can put the aldehyde, because the aldehyde has to be on carbon 1. But I can shift this OH to a carbon where it wouldn't make it chiral, and that can only be the end. So I'm going to put my OH on the end, fill up the H's there. Okay. Right, a branch chain isomer. So again, I've got 4 carbons. So the only way I can do a branch is to go like that. We also have to have the same functional groups. So I'm going to put my aldehyde where it has to go. And it does not have enantiomers. So I'm actually going to put my OH here because that's going to give me this carbon has got a two CH3s coming off it. So those 2 are the same. That's only got 3 things, and those have got 3 H's. I do think there was another option for that one. I'm just going to draw this one. An isomer that contains the ester functional group and no branch chains. So I'm going to draw my ester in the middle. And I'm just going to make sure there's 4 carbons. It doesn't matter where I put them, so I'm just going to put them like that. No branches. I'm just going to double check that I've got the right number. Have I got 4 C's, 8 H's, and 2 O's? 1, 2, 3, 4, 2, 1, 2, 3, 4, 5, 6, 7, 8. Yep, good. And an isomer that contains a functional group that would rapidly decolorize bromine water. So my isomer's got 4 carbons. And to rapidly decolorize bromine water, I need a double bond somewhere. It doesn't matter where it goes. I still have to have this molecular formula, right? So I need 2 O's. If I try to put an aldehyde or anything like that in, I'm going to not have enough hydrogens. So I just need a couple of OHs. They can go anywhere, okay? Right, so that gives me my answer there. You could have put the 2 OHs anywhere. You could have put the double bond anywhere. Right, over here to compound K, we need a 3-step reaction scheme to convert J to K with our reagents, etc., etc. Okay, so if we look down here at K, we need to oxidize this, and we need to convert this into an amide. Right, so to convert this into an amide, we actually need to convert it to a carboxylic acid, and then to an acyl chloride, and then to an amide. So that's pretty tricky, this question. So I'm actually going to start by adding Cr2O72 minus /H plus /heat. And if I do that, I am going to get, excuse me, I'm just having a look here. I could have chosen MnO4 minus /H plus and heat there. So what I get there is I'm going to keep my carbon chain. So I've got 4 carbons. Everything that can be oxidized will be oxidized. This will be oxidized, and this will be oxidized. Okay, and then I'm just going to continue. That's all that these don't need an extra hydrogen. Okay, so now if you look at this functional group here, it's exactly what we need. This one now needs to be converted into an amide. So what we actually needed to do was PCl5, that one, or SOCl2 or whatever, and that would substitute the OH. So the carbon groups stay the same, doesn't affect the ketone. Okay, and then the last step is I'm going to add my ammonia, which will substitute for the Cl, and it needs to be alcoholic or concentrated. Okay, that was a bit of a tricky one. Well done if you got part or all of that right. Okay, question 3, we're up to our polymers question. So we need a repeating unit, so that's one of these and one of these. It's drawn very nicely for us. We need to condense the alcohol and the carboxylic acid group to make an ester group. So remember, we're going to take the OH off the carboxylic acid, and we're going to take the H off the alcohol. Okay, so I'm just going to do that, and that's going to be removed. So all going to be removed. So I'm going to copy these two with those atoms removed. So O, C, H, CH3, C double bond to O, and then I'm going to join this one in here. O, CH2, C double bond to O, and then I'm going to dot, 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 dot that one there. All right, explain the reaction that's occurring during the polymerization. In your answer, you should, right? So we should be describing condensation, and we should be just saying how condensation is when two things are joined with the removal of a small molecule, in this case water. You should be describing polymerization, and you should be saying that a polymerization reaction is one where you have long chains of many repeated monomers, and in this case we have 2 different monomers. You could have even used the AB type, so monomer A, monomer B, and so in our polymer we go A, B, A, B, A, B. You should have described the functional group changes. So we've got a carboxylic acid and alcohol functional group combining to form a new ester functional group for every monomer that gets linked. And we've talked about the polymer, right? So that was pretty straightforward. And here we've got two reaction schemes that we need to compare and contrast. Both use the same reagents, both start with the same reactant, but they're used in a different order. So conc H2SO4 is a dehydrator, so we're going to eliminate up here. So we're going to keep our 4 carbons, and we're going to make a double bond there, and the aldehyde is not going to change. So there. Adding hydrogen is going to put hydrogen in across this double bond. So we're just going to end up with our aldehyde. And NaBH4 is our reducing agent. So it's going to reduce this to an alcohol, sticking with our 4 carbons and ending up with an alcohol. Okay, so quite a few of you got that. Good job. Set B, we're going to start again, but this time we're going to reduce. So NaBH4 only reduces aldehydes. It's not strong enough to reduce a carboxylic acid. So we've still got CH2OH, CH2, and then we're going to have CH2OH again. This was the bit that got a lot of you. We've got the dehydration next. But the dehydration is going to dehydrate that OH and adjacent hydrogen and that OH and adjacent hydrogen. So what we're going to end up with here is we're going to end up with a compound with 2 double bonds, right? So we've actually eliminated 2 OHs and adjacent hydrogens. So then when we hydrogenate, when we add in our hydrogen with our platinum catalyst, we're going to add in hydrogen there and there and there and there. So we get to 4. So the end products do differ. So we needed to compare and contrast. The idea was in the end that you actually, because you did them in a different order, you actually ended up with a different product. But a lot of you ended up with the same product because you forgot to eliminate both OHs there. So that was a little bit of a sticking point. This was a bit kind of vague in here, but if you got this right, you actually generally did a good job on that. And that was the end of the paper. Ooh, short and sharp. I think the organic paper was probably the pick of the bunch there. Again, hope everything's going well, and I will see you after the holidays. Ka kite.